So I want to report on a joint work with Colin Faverjon. So it was supposed to be on the archive today or yesterday, but I failed to put it on the archive, so it will come soon. Before speaking on Mahler's method, I want to start with some problems, mainly two problems, which are related to the representation of both natural numbers and real numbers in integer bases. And mainly I'm interested in questions of base change. So what happens to these representations when you go from one base, say 2, to another base, say 10. So we start with natural numbers. And we know that some special set of natural numbers are very simple expansion in some given base. So a very basic example is a set of powers of 2, which are here represented in base 2. So, and I put the term here simple, and the theory of finite automata is useful to formalize this idea of what simple sets are. So the set of power of 2 is said to be recognizable in base 2 or 2 automatic, and this means that you have a finite state machine. Here you have only 3 states whose ability is to read any numbers written in base 2. So you start from the initial state here, and then you can read the expansion of n in base 2. And after the reading of this integer, you will end after in set A or B or C. And you are a power of 2 only if you end the reading in set B. And I give an informal definition, but as well you can define what a Q automatic set is, as long Q is an integer at least equal to 2. So it means that you have such finite state machines that can recognize among all the integers those who belong to your set. Okay? And the kind of question I want to consider is, now if you consider the powers of 2 in base 10, they are here on the right-hand side, it seems to be much more difficult to recognize them. So if I give you power of 2 in base 10, it's harder to figure out how to recognize this power of 2. And actually, power of 2 are not a 10 automatic set. Okay, so you cannot design a finite state machine to recognize them. So this led in 1969, Cobham essentially solves this question. And there is a fundamental result from automata theory saying that if the 2 bases are multiplicatively independent, like 2 and 10, it's essentially impossible to be, for a set of natural numbers, to be Q1 and Q2 automatic at the same time. So the only sets that have this property are the periodic sets, so those that can be written as a finite union of arithmetic progressions. And those are automatic in any base, so an arithmetic progression, you can recognize whatever the base you choose, but these are the only ones, kind of trivial set. So the first problem I'm interested in is a kind of stronger version of Cobham's theorem, but written in more algebraic terms. So we consider several pairwise multiplicatively independent natural numbers and several automatic sets, and none of this set is trivial, so none can be written as a finite union of arithmetic progression. So then the conjecture, the problem is to prove that the corresponding generating functions are always algebraically independent. So we move from this question of representing natural numbers to a question about transcendence and algebraic independence of functions. And so it looks like a rather difficult question, which is only solved in the case R equal 1 up to now. So if you have only one set which is not finite union of arithmetic progression, the generating function is transcendental, so it's quite easy results. But otherwise, it's still open. Only specific cases have been handled so far. So this is our first problem. And the second problem I'm interested in is in a similar spirit, but we move from natural numbers, set of natural numbers, we replace them by real numbers. And again, finite automata can be used to define what simple real numbers are. So we will say that a real number psi is automatic in base B if its base B expansion can be generated by a finite state machine. So by generating, we mean that we choose another base and we feed the machine with the integer n written in this base, and then the machine will output the nth digit of our number. So here is an example, so the Tumors number. So it's a number written in base 2, and if you want to know what the nth digit is, so you write n in base 2, you read n with this automaton, and if you end the reading in A, so the nth digit is 0. If you end the reading of n in B, the nth digit is 1. So it provides an infinite world, an infinite sequence, which is not periodic. So the number 2 is an irrational number, which is called automatic in base 2. And from the computational point of view, these automatic numbers are the simplest computable numbers we have. Okay? Yeah.
Just understand. How should I understand this diagram?
This?
Yes.
So it means that if you give me an integer n, you write it in base 2. So you get a finite world with only 0 and 1. So now you start from the first state, A, and you start reading, say, from the left to right, but it's similar. You can design another machine if you read from right to left, but let's say you start with the most significant digits, and then you start reading. So perhaps the first is a 1, and then you have a 0, and then again a 0, and a 1, and a 0, and a 0, and a 1. So you read these finite words. At the end of the reading, you are either in set A or B. Depending on that, the nth digit of the Tumors number will be a 0 or 1. So if you consider this automaton, what is doing is computing if in your number n, if there is an odd or even number of ones. So, if the number of ones is even, you will end in A. If the number of 1 in the expansion of n is odd, you will end in B.
Sorry, I'm confused by the n. So the n is not the same n. The nth digit, you have the number n and you have the nth digit.
Yeah. If you want to know what the nth digit is, you feed the machine with n.
Oh, n. Oh, it's the same.
So, but the machine, you can feed it with all the natural number. So you start with 0, then 1. 0, it gives you the first digit. 1, it gives you the first digit. Then you write 2 in base 2. It gives you the second digit, and then you feed the machine with 3 written in base 2. You get the third digit, and so on. So like this, you compute the digit successively of your number. Okay?
Just to clarify myself, I mean, every digit, sorry.
Yeah.
Every digit can be computed independently of all the other digits.
Yeah, in that case, yes. Yeah. So we have similar questions with the natural numbers, but I have to say that usually they are much harder to handle. So the situation is with natural numbers is usually difficult, and here it's even harder. So for instance, one of the questions people have is, if you start with the expansion of a classical constant like square root of 2 or pi, which can be easily defined in geometric terms, in contrast, we don't know many things about their digit expansions. And one of the main conjecture in the subject is, of course, we expect that the digits are chaotic, but we are so far from proving that a first, more reasonable question is to prove that none of these classical numbers, and I could add many to this list, can be automatic. So whatever the base you choose, 10 or 2, you expand square root of 2 or pi, you do not expect to have a simple sequence like the tumor sequence. So, but even this seems to be really hard to prove, and actually it is only known for a number like square root of 2. So in a joint work with Jan Bugeaud, we proved now more than 10 years ago that the base B expansion of any irrational algebraic numbers can never be generated by a finite automaton. But it is not known for e, pi, log 2, or zeta of 3. Okay? But it is conjecture that these numbers are not automatic. So the strategy we used with Jan Bugeaud was based on the subspace theorem of Bogdan-Schmidt, and I will say a word on this later. But the problem we are interested in here is what happened to these tumors numbers if I written it in base 10. So now the digits which are so simple in base 2 seems much more unpredictable. Okay, so, and we would like to prove something in this direction. So we have a first problem which looks like Cobham's theorem, which would say that if I choose two multiplicatively independent bases like 2 and 10, a number cannot be automatic. So this expansion cannot be produced by a finite state machine in these two bases unless it is a rational number. So if you have a rational number, the expansion is eventually periodic, so it can be generated by a finite state machine in any base. Okay? It's like arithmetic progression, but for real numbers, we have these rational numbers. Okay? So it is an open problem, and probably rather difficult. And the second problem is even worse. So it's like the first problem I mentioned, the generalization of Cobham's theorem. So now if you pick several numbers, like the tumor numbers, but which are automatic in multiplicatively, pairwise multiplicatively independent bases, and if none of which is rational, so they are all transcendental, then they should be algebraically independent over Q bar. So the Q bar means the field of algebraic numbers. Okay? So we do not expect any relation between automatic numbers in different bases. So if you have so which means that these tumor numbers in base 10, not only it is not 10 automatic, so it is not automatic in base 10, but it is really far from being, because it should be algebraically independent with any automatic numbers in base 10. So again, this problem is only solved for r equal 1. And this is a theorem AB I just mentioned with Jan. If r equal 1, so we have one number which is irrational and generated by a finite automaton, and it should be transcendental. And this is theorem AB. Okay, so these are our two targets. And now I want to move to Mahler's method. So what is the connection with Mahler functions? So first I recall what are these Mahler functions. So we have an integer q at least equal to 2. And Mahler functions are solutions, so they have algebraic coefficients. This means that they are analytic function converging in some neighborhood of 0. Of the origin, and Mahler function f of z is a Mahler function if it satisfies such a non-trivial linear difference equation with respect to the operator z gives z to the q. Okay, so we have a linear difference equation, and we are considering the solution. It's important in Mahler's method that we consider only analytic solutions. So example like log z or log z are not doesn't fall under the scope of Mahler's method. And we are interested in this because already in 1968, Cobham makes the following connection between automata theory and Mahler's function. So if I have an automatic sequence like the tumor sequence, so it's generating function. So if the sequence is Q automatic, the generating function is a Q Mahler function. Okay. So all the problem I mentioned about automatic numbers or automatic sequences, automatic sets of natural numbers, they now can be rephrased as statement and also extended, because the converse is not true. So you have Q-Mahler functions that are not generating function of automatic sequences. So all our problems can be restated and extended in problems about the algebraic relation between the values of Mahler function at algebraic points. Okay? So because, for instance, if I want to know the tumors, imagine I take the tumor sequence, and I want to speak about the tumors in base 2, so it's just the generating function at the point 1/2. So the numbers I'm interested in here appears as values at algebraic points, actually at rational points of Mahler functions. Okay, so now what we know about Mahler's function. If we want to study linear equation, it's like with the theory of differential equation, it's more comfortable to move the equation to linear systems. So we will study the linear Mahler system. So of course, if you have a vector solution to such equation, so we have a matrix with rational coefficients, which is invertible, and we are considering vector of solution with analytic coordinates. And the function here that are solution of such systems are all Q-Mahler function. And if you have a Q-Mahler function, it can appear as a coordinate of a vector solution of such systems. Okay, so you can move from one setting to the other. So what we expect about this such system? So first, there are some special points. It's like with differential equation again, which are called singular for the systems, and these are the points whose orbit under the transformation can fall into a pole of the matrix AZ or a pole of the matrix A minus 1Z. By pole of the matrix, I mean pole of one of the coefficient of the matrix. But outside these special points, the guess is that the algebraic relation between the function f1, fm of z at algebraic point are totally governed by the algebraic relation between the functions themselves. So this is the idea of Mahler's method. It transfers the relation between numbers to relation between functions. And in this direction, in 1990, Nishioka proves that if I pick a point, an algebraic point, between 0 and 1, because otherwise the Mahler functions are basically meromorphic on the open unit disk, and the unit circle is a natural boundary, so it's natural to look at a point where the function is defined. If it is a regular point, then she proves the equality of the transcendence degree between the values and the function. So, which means that quantitatively, there is no more relation between the values and between the function. And of course, if you have an algebraic relation between some functions, you can specialize this relation to get an algebraic relation between the values. So this is more or less the best we can hope. But this result has also some deficiency. For instance, imagine that I'm just interested in one function, okay, at one point. And I know that this is a Q-Mahler function which is transcendental. So all what I know, so I know that it can appear in such systems, but all what I know is that the transcendence degree on the right-hand side is at least 1, because I have one transcendental function. But on the left-hand side, so I will have that at least one of the number is transcendental. But I'm not sure that this is, if the function f1 is transcendental, I'm not sure that f1 of alpha is transcendental. Perhaps this is another number. This is a real trouble for application. And recently, Philippon proved, Patrice Philippon obtained the following important refinement of this Nishioka results that I'm going to describe. So you consider a solution to a linear Mahler system and a regular point, and now you pick any homogeneous algebraic relation between the values f1 of alpha, fm of alpha. So the statements say, so actually the version I'm quote here is slightly stronger than the one was obtained by Philippon, and this is a version I obtained with Colin Faverjon in another joint work. So it says that if I have one algebraic relation between the values, then there exists another homogeneous relation between the functions. Okay, so we have one relation between the function such that if I specialize the variable z to alpha, I get my first relation. So it means really that any relation between the numbers, imagine I have a quadratic relation between these numbers, then I have a quadratic relation between the functions, such that if I specialize at alpha, it gives me my relation. So it's clearly the best you can hope. Any relation, so it replaces Nishioka results is kind of quantitative results, and now this is a qualitative result that take care of any relation. I should also add that this result was motivated by other previous results that was obtained in the context of Siegel E functions by Szydlowski, Nesterenko and Szydlowski, and more recently Beukers and André. And they obtained exactly the same result. So the result I mentioned, Nishioka theorem, is the exact analog of the Siegel-Szydlowski theorem, and this one is an analog of the theorem of Beukers that was also reproved by Yves André. Okay, so now when you have this theorem I call lifting, because any relation between the values can be lifted at the level of the function. This lifting theorem has some very nice consequences. I put the two main ones. So first, now you consider a Mahler function, so a solution of a Mahler equation, and you assume that the coefficient belongs to a number field k. So this is always the case because of the equation that the coefficients are confined in some given number field, but I call it k. And you put any number, algebraic number alpha, such that the function is well defined at alpha, then either alpha belongs to the small number field k of alpha, or it is transcendental. So there is no more question about a regular point, or it's true for any point, any algebraic point, and any function. So this is the strength of this result. For instance, if the coefficients are rational numbers, and if the point is rational, then you get that the values is either rational or transcendental. Okay? And secondly, there exists an algorithm so that if you give me one function and one values, I can decide whether the values is transcendental or not. So you have to imagine that the difficult question of proving transcendence is now like a routine computation. And again, these two results were exactly the same in the theory of E functions. Okay, so now the two theories reach exactly the same level. I don't speak, of course, about the concrete algorithm, so you just care about existence of the algorithm. I don't claim that I have implemented an algorithm, but anyway, such algorithm exists. So this, the point one provides a new proof in particular and an extension of the theorem AB. So the fact that square root of 2 cannot be generated by a finite automaton. So it's easy to see. But as strong as the lifting theorem is of just no help to solve the three problems I mentioned at the very beginning of the talk. Okay? And this is why we need Mahler's method in several variables. So what is this? So now we are considering analytic function in several variables. And instead of looking the action of z give z to zq, we consider a matrix with integer coefficients, n by n matrix, and we let act this matrix multiplicatively on numbers. So exactly like this. And then we consider linear T-Mahler system. So T is a matrix transformation, and we consider exactly the same kind of systems, but now with several variables. And again, we hope that if we choose some suitable algebraic points, now in Cn, the algebraic relation between the values of such solution to such systems should be governed by the algebraic relation between the function. Okay? And in 1982, Loxton and van der Poorten, so they claim to prove such results, so like the Nishioka theorem, so that the transcendence degree of the values is equal to the transcendence degree of the function as soon as t and alpha satisfy some condition. I just don't want to speak about them, but essentially you can argue that these conditions are necessary for Mahler's method can work. So they are quite natural conditions, but a little bit technical to explain. And the main constraint is that they assume that the matrix here of the system is well defined and non-singular at 0. This is the main restriction. But the point is that the proof is not complete. There is some gap in the proof, even if the strategy looks good. And so in the end, the results, the equality of transcendence degree has only been proved for special class of matrices. So this was reported, for instance, in the book of Nishioka, essentially when the matrix is constant or when the matrix is diagonal. So diagonal means just several equations of order 1 putting together, and it's well known that order 1 equations are always much simpler than the general equation. And constant equations with constant coefficient are also quite specific. So the result we proved with Faverjon, our first result is concerned with this general equation, but I just want to explain why it's so important to use Mahler's method in several variables. If you consider the simple Mahler function z to the 2 to the n, so it satisfies the inhomogeneous order 1 equation f of z2 is equal to fz minus z. Really easy. So using Mahler's method in one variable, for instance, the Nishioka theorem or the lifting theorem, so we know that at the point 1/2 and 1/3, the value is transcendental. But you cannot use the lifting theorem to speak about the values at 1/2 and 1/3 together to look at whether they are algebraically independent or not. But what you can do is to associate with these two values the following two variables Mahler systems. So I just put the equation in Z1 and repeat the same equation in Z2. So now I have two Z1, Z2 Mahler functions, but actually one is only with Z1 and the other is only with Z2. And the transformation matrix is just 2, 2. So it's a very simple case of matrix transformation. And now the point is that, it's really the key point, is that you know that the function f is transcendental. So you get for free that f of Z1 and f of Z2 are algebraically independent. Okay, they cannot have any relation because they have not the same variable. So it means that if I look at this solution, so the transcendence degree of the function is 2. So the transcendence degree of the value should be 2. So if the trick works, I get that the two numbers are algebraically independent, and I don't have to care about the algebraic relation between the function. I get it for free. Okay? So, but I should say that this trick works, but imagine that I choose, so I will apply at the point 1/2, 1/3. But imagine you want to apply the same trick at the point 1/2, 1/2. You get that f of 1/2 and f of 1/2 is algebraically independent. So the trick cannot work always. So what you need is that the coordinates are sufficiently independent. So this is part of the natural condition we have in Mahler's method in several variables. Okay? But it shows you how this formalism is powerful to prove algebraic independence. So the results first result we obtained with Colin is a proof. So it's a lifting theorem for the so-called regular singular system. So it is exactly as Philippon's theorem. So any homogeneous algebraic relation can be lived to an algebraic relation of still homogeneous that specialize at your relation. So it's exactly the same. The condition here that the point is regular and the pair is admissible is exactly the condition Loxton and van der Poorten had. So I say natural condition, I don't want to speak about them. So the only restriction is that the system has to be regular singular, which means that, so in the framework of differential equation or difference equation, for instance, difference Galois theory, it's quite natural. So it means that you can perform a gauge transform that make your system constant. The matrix will become constant. And for the gauge transform, you allow that the function in your big matrix phi are ramified generalized Laurent series. So it's kind of meromorphic functions, but that can also ramify. But you can just don't care about this definition. A point is that, in particular, if the matrix is well defined and in non-singular at 0, the system is regular singular. So it is an extension of the condition in Loxton and van der Poorten. So basically, we restore the proof of Loxton and van der Poorten and extend it to this more general class of systems, and also get this finer conclusion. Okay, so this is the first result. And we also have a second one I want to mention, which is of a completely different type. I think for me it's the first time I see a result of that type in such a general setting. So it's the following one. So if I have a finite set of complex numbers, so I will write alg E for the ideal of algebraic relation between my numbers. And now if I have if I partition the set E into several subset EI, I denote by alg EI with respect to E the ideal generated by the algebraic relation of the member in the subset EI in the larger set of polynomials. So which means that there are all the algebraic relations that only concern the element of the set EI in some sense. Okay? So I call this the pure algebraic relation with respect to the partition. Okay? So you have the general, you can imagine that you have some really algebraic relations that concern all the numbers, and some are pure if they are made with just element of some subset. So for instance, if there is no relation between the number EI, so alg EI is 0, and so this one is also 0, there is no pure algebraic relation. And so the second statement we get is the following one. So I will end on this slide. So now you can pick several Mahler systems in several variables, and we just assume that they are regular singular, and for each system we choose different points such that the lifting theorem applies. So our first theorem can be applied, and then if the transformation are sufficiently independent, so which means that their spectral radius are multiplicatively independent, we have the following results. So pick any finite set of values in each system and consider the union of these values. Then the algebraic relation between the whole set of values is generated by the pure relation. So this means, for instance, that if in each system I pick just one number, which is transcendental, then all the numbers I get are automatically algebraically independent. Okay, so this statement really is a statement about algebraic independence. Okay, so if I pick in each system several values for which I know that they are algebraically independent, I will get algebraic independence. And just to conclude, I would say that these two results have an implication on the three problems I mentioned, and they actually would solve the three problems if we do not have this restriction to regular singular system. So if you pick a system at random, it will be regular singular. So it's a generic property to be regular singular. But if I start with some automatic sequences, I'm not sure to get regular singular systems. So we are still not able to fully solve the three problems I mentioned at the beginning, but it's still a significant progress on these three problems. So I stop here. Thank you for your attention.
Could you show me an example or applications of regular singular Mahler system of several variables?
You want to see
Examples.
So, for instance, if you imagine that you consider the Fibonacci sequence. Okay, so Fibonacci sequence, it is given by following morphism: 0, 1 gives 0, 0 gives 0, 1, 1 gives 0. So starting from these rules, you can generate it an infinite world like this. So 0 gives 0, 1, 1 gives 0, 0 gives 0, 1, 0 gives 0, 1, 1 gives 0, 0 gives 0, 1. And you get a non-periodic sequence, which is called the Fibonacci sequence. So now if you consider, so let us say that the nth term is an, so if we consider sum of a and the n, so we get an interesting function. So for instance, we would like to prove that this number is transcendental or is algebraically independent with the two most numbers or things like that. But if you consider this generating series, it is not expected to be Mahler functions, okay? But it is two variable Mahler functions. You can start with a two variable Mahler function f of z1, z2, such that if you specialize at zz, you will get your function phi of z. So, and if you consider the system, so here, basically this function phi we could be interested in will appear as a specialization of a two-variate Mahler function. If you look at the system associated with this, it is singular at 0, but the matrix is regular singular, so you can find this gauge transform. So, but it's a little bit long to write on the system, but this is one example. The same occurs if you consider the Fibonacci, like 0 give 0, 1, 2, 1 give 1, 0, 2, and 2 give 0. So you have plenty of morphism like this we would like to speak about, which are not concerned with Mahler function in one variables, but appear as specialization of Mahler function in several variables. So I could give you precise examples.
Thank you.
Okay.
So, some more questions? No? So, let's thanks again.
Thank you.